Hello and welcome to a tutorial on the RoPE software. I am showing RoPE on version 10.15.7 of Mac OS. This is the minimum version that RoPE can be run on. So I have the RoPE installation in my dock here. So if I run it, project menu. So this is asking me to either choose an existing project, I don't have any at the moment, or find a project folder in which we can work. So I've already created this folder in my user directory. So I can choose this option, and I'm going to go to haemoglobin here, and I choose this directory. I'm going to choose a project name. I'm going to call it haemoglobin. And that is how I would be able to access this project after I've reopened RoPE. So I can create that project, and now we're in the main menu. This menu is split into the file manager, the protein entities which have been defined within RoPE, the models of specific proteins that we've had from, for example, data collection, and metadata, which is information that you have about your models from external sources. So if we look in the file manager, there's nothing here at the moment. It's completely empty, a new folder. We can press the back button, and now we can go to protein entities. So what we want to do is define two protein entities which make up haemoglobin. That's the alpha subunit and the beta subunit. In order to do this, we can click on the Add Entity button. We have a number of options here. We can get the sequence from the UniProt ID, from the FASTA file which we may have provided, or we can indeed type in a sequence. We're going to take the UniProt ID. Now, in order to find out what the UniProt ID is, I've gone to a structure of deoxyhemoglobin here, and this contains the UniProt IDs for the alpha subunit and for the beta subunit. So here we have the alpha subunit P69905. So we can enter that in here, P69905. I don't have a shift key, so just go with a lowercase p there. And it will download the sequence from UniProt, and then you can give the entity a name. So we're going to call it the alpha subunit, and we can create that. That's the alpha subunit. We can do the same thing for the beta subunit. So we add an entity from the UniProt ID. This time we're getting P68871. So we can type that in here. And we can call that the beta subunit. Now that we've loaded in the sequences for the alpha and beta subunits, we can start to download PDB files which contain these entities. So if we go to one of these entities, like the beta subunit, we're given a series of options here. So we can have a look at the sequence, which is in this view. And if we go back, we can't look at the RoPE space yet because we don't have any models. The next option is to search the PDB for examples of this entity, which is what we want to do. So if we click on this, we are given some options. So for the purposes of this tutorial, I will keep the sequencing identity cutoff at 98%. The option to return a particular number of structures is default 500. If you feel like your computer would rather run 50, then I would change it to 50 here, but I'll leave it on 500 for this tutorial. So when I press run, it then retrieves a list of PDB files from the protein data bank, and these PDB files will be downloaded from PDB redo if it is available. And to do that, we can click this download button and confirm that we would like to get these PDB files from PDB redo. The download runs in the background, so you won't be able to see when they're finished, but you can get an idea of the speed because they are marked as downloaded as they are brought into your file system. And if we now go back all the way to the home page and look at the loaded files, we can see that they're starting to appear here. Now that we've downloaded the files, these are not yet turned into models. So models are descriptions of PDB files in the RoPE format. And at the moment we don't have any. From either the entity menu or the model menu, we can click this toolkit button here and press auto model. So that's going to go through each of the PDB files, and it will have a search for the sequences within those PDB files and assign any entity which matches those files to within 80% sequence identity. So we can have a quick look inside one of these models. We have the initializing file, which is the PDB file. The model name is given the file name without the file extension. We have a chain assignment, so if we go in here, it'll tell us what chain numbers are available. This is clearly not a full hemoglobin. We have an alpha and beta subunit and 2 unidentified subunits from some other protein entity. And we also have metadata here listed. At the moment it's empty, but it is possible to associate metadata with each of these models. So I will allow the auto modeling process to complete and then come back to you. Now that we've created these models, we can go back to the entities. So now we have a series of models listed for the alpha and beta subunits, roughly the same. If we enter one of these entities, now we are able to see that we have 505 molecules which have been identified over 240 models. This is taking into account the fact that a single PDB file could have multiple chains of the same molecule. If we now click on RoPE space, we'll be confronted with the fact that we have 505 unrefined molecules, and it will ask you if you want to refine the torsion angles to the atom positions that were in the PDB. We're going to click yes, and then it will ask us how many threads we would like to use. Because I know that my Mac has 6 cores and I need at least 1 free in order to power the GUI and other things that I want to do with my machine, I'm going to choose 5 threads, leaving 1 core free. And so when we press OK, it's going to start going through each of the hemoglobin molecules and refining them. Each one of these threads takes a different model, so it's able to work on 5 polypeptide chains at the same time. We can see here what RoPE is actually doing. What it has done is loaded each one of these polypeptide chains using the bond lengths and angles as described in the geometry library, and the torsion angles have been estimated by taking each sequential set of 4 atoms and calculating a torsion angle from those. This is actually not a very good estimation of where the protein chain should go, because tying up a protein from one end to the other is a recursive system. This means that any small error in the torsion angles will get propagated and send the protein chain off in the wrong direction, and this compounds on every bond that you go through. So what RoPE is doing here is taking the polypeptide chain and adjusting the torsion angles in order to bring the path of the polypeptide chain back on the original atom positions which were described in the PDB file. And what you're seeing is an updated cartoon view of how this refinement process is going, just to watch. And that is the output of thread 0. So this is going to take a while, so I would recommend that you have a cup of tea and a break, and I will come back when this refinement process has been completed. So refinement is complete. On my computer it took just under an hour. If we click this save and return button, then it will save all of your progress so far and then return to the previous screen. Before we go back to the results, I just want to recap what RoPE is doing behind the scenes here. So we've loaded in a bunch of PDB files, and from those we can extract the protein sequences. We also have the atom positions, and we can use those to optimize the torsion angles. Now we can combine the two, so we can collate all of the torsion angles associated with the sequence. And because earlier we introduced the reference sequence, we can also align each of those sequences to the reference, and that allows us to account for gaps or insertions or mutations. Then we can combine these two to collate all of the torsion angles, so every residue has a list of torsion angles associated with the main chain and the side chain. We can linearize that table, so every row has a molecule and every column is a residue torsion angle pair. We can then focus on looking at the differences of the torsion angles in this table, and we can do that by calculating an average, and then we can subtract that average from each of the structures, and this gives us a list of difference torsion angles. For each one of those molecules, we can calculate a correlation coefficient by comparing the torsion angles, and then we can insert each of those correlation coefficients into a correlation matrix showing the correlation between each pair of molecules. We can then run singular value decomposition on that correlation matrix, and this gives us a plot where every dot is corresponding to a protein chain, and also similar conformations tend to group together. So this is what we're going to have a look at for haemoglobin. So now we have returned to the RoPE software. There's been a bit of a break in recording of the tutorial, and now this is a later version which is full screen on a Mac, so hopefully that explains the differences. Now the analysis has been run on all of the structures, and we're a bit zoomed in at the moment, so the controls for navigating the space are the same as those in Qt. So a right click and forwards and backwards mouse movement allows you to zoom this window. Left clicking and dragging allows you to rotate the view, and if you press Control and then drag, then you can pan the view. So this is the RoPE space for haemoglobin. We can see that it roughly divides into two sections, but we don't have any metadata here, so we don't know really what distributions to see in this clustering. So in order to add the very basic metadata, we can go back to the entity menu and press add metadata, and we can ask for metadata to be downloaded from the protein data bank. So that's what we're going to do. And then it picks up a number of categories of metadata from the PDB. So if I show you them here, we have a few of the usual suspects that you may want to look at from the PDB and the title of the PDB file. RoPE has an internal database where it saves all of the metadata. So once we've downloaded the metadata, we then need to add to the central database, and this will make the metadata available in the RoPE space. So if we go back now to the RoPE space, and we have the same plot as before, but now if we go to the rules option in the top right hand corner, we can add rules to color or change the icon of the individual proteins in the RoPE space. So if we click add new rule, then we can vary the color. One of my favorite things to start with is to vary the color by the resolution. So this will change the color. If we go to the options here, then we would have the option of changing the minimum and maximum values, but I'm going to keep them the way they are. And if we now create this menu, press OK, then when we go back to the previous slide, then it will color by resolution. So we can see that the highest resolution structures tend to be at the bottom of this plot, and then there is a significant reduction of resolution to the top and in the middle of this distribution. There are other rules which we can make. So for example, if we go back to the rules, we can change the icon depending on the space group. So this allows us to see the distribution of the conformations of the protein with respect to the space group. And if we want to change the icon on the space group, then we need to enter the options. As a default, it will change the icon if there is a space group, and every crystal does have a space group. So we need to go into the options and specify that we should only change the icon when the value is one of the various space groups. So let's choose P21212, as it has a decent number of structures associated with it, and press OK, create, and OK again. And now we're going to have a star icon for all of the P21212 conformations, and we can see that that occupies a distinct location in the RoPE space. So there are lots of ways of playing. I will hopefully make more tutorials, particularly for loading in your own metadata and the various other functions in RoPE, but hopefully this will get you started and being able to play.